General relativity. Consider this: inertial versus gravitational mass. Mass has two seemingly different properties: a gravitational attraction for other mass in Newton's law of gravity, and an inertial property that resists acceleration. When you think about it, we've been using mass interchangeably, and we've been using it in all these equations through physics up to this point, but these are really different properties. If I think about inertia, that is the resistance to my change in motion, and we associate mass with that. Gravity is a force. It is a force between two masses, and those quantities are proportional to the force between them. Totally different concepts. So we've been using them interchangeably, but they should be different. At least we thought up to this point. Einstein's view that this dual behavior of mass was evidence for a basic connection between these two different types of behavior. In fact, he said no experiment of any kind could distinguish between these two types of masses. As usual, Einstein is taking complicated ideas and trying to make them simpler in a much easier to realize format. It's kind of a precursor to what the great things that are about to happen. Equivalence. Einstein's happiest thought. In 1907, Einstein has what he called the happiest thought of my life. What is the happiest thought of Einstein's life? That's a good question. Was it his marriage to Mileva, the woman who was working at the same university as he was, and also a very great mathematician? They got married, had some kids. No, that wasn't the greatest thought of his life. Was it his second marriage to his cousin Elsa? No, even though Elsa was a great cook, he doesn't look to be very happy right here. Was it receiving the Nobel Prize from his mentor Max Planck in 1921? That should have been the greatest moment. But no, that was not the happiest thought in his life. In fact, at that time, some stories say that he had promised to give the Nobel Prize, which in the money of today's dollars would have been worth more than $1 million. He was to give that to his first wife, Mileva, so that she would allow him to divorce, and then he could marry Elsa. So that was part of the idea there. No, it wasn't that. Einstein's happiest thought, the happiest thought of his life in 1907, was that if he were falling off the roof of a house, the gravitational field would not appear to exist. In other words, he would appear to be weightless. If there was a scale underneath him, he could look down that scale, which is falling at the same rate that he is, and he would register 0 weight. What a happy thought. So in that frame of reference, he would be weightless. Similarly, if he were in an elevator or a spaceship out in space, and the spaceship were accelerating, it would measure some weight on that scale. And at that time, when he's accelerating that spacecraft, he would not be able to determine whether his weight was due to the acceleration of the spacecraft or whether he actually did have weight. So he would not be able to tell whether his weight was due to gravity or the acceleration of the spacecraft. How about that? This is really a profound realization, and it was something that he was able to extend further into some neat results. Take a look at this. Suppose you were in an elevator. An observer's in an elevator on the surface of a planet. You're in a gravitational field, and gravity's pulling down towards the center of the planet. You feel pressed to the floor due to your weight, due to the gravitational force. If you were to release your briefcase at that moment, it would fall and accelerate down to the floor with an acceleration equal to the acceleration of gravity. So the acceleration of gravity would pull your briefcase down to the floor. Let's say you're in a second elevator, closed elevator, you can't look outside, and the elevator itself is accelerating upward with some value of acceleration equal to the same g that we've just been dealing with. You're pressed to the floor as before, and you feel like you weigh the same as you did before. As far as you're concerned, you can't feel any difference. The elevator is closed, you can't look outside. The fact that the elevator is accelerating, the frame of reference is accelerating, makes you feel like you have weight. And if you were to release your briefcase in that instant, it too would accelerate towards the floor, at least in your frame of reference, with the same value of g that you had when you were stationed in a gravitational field. In fact, you wouldn't be able to distinguish between the second instance of an accelerated frame of reference and the first instant of being located in a gravitational field. There's no way you could tell the difference. Conclusions. Einstein claimed that these two situations were indeed equivalent. No local experiment could distinguish between the two frames. One frame is an inertial frame in a gravitational field. The other frame is an accelerating frame in gravity-free space. How about that? Well, this may seem obvious to you. I mean, we've had these kind of situations. We deal with elevators every day in our life, and we know we feel like we're way more when the elevator is going up. But in Einstein's day, elevators were not so common to begin with, and also to make this association between acceleration and gravity is actually quite profound. Even though it seems easy, it's going to have quite dramatic effects on how we view other things. For instance, light. Consider this. You're back in the elevator. You're observing this frame of reference, and someone from the outside comes in and flashes a beam of light across your elevator. You see this beam of light, and it looks like it passes in a straight line through your frame of reference. If your elevator is at rest, you will see this beam of light travel in a straight horizontal line, no problem. What happens if you're moving in an elevator at constant velocity and the same fellow outside shines the same beam of light? In this case, the beam of light still follows a straight path, but it follows a path that seems to be going at an angle. In any case, it's still following a straight line path in your frame of reference. Well, let's say you're in the same elevator and you're accelerating now past the beam of light. Well, the beam of light that you witness now, as your frame of reference is accelerating, the beam of light is going to be curved as you're going and increasing your speed through that zone. So the light will curve, but the equivalence principle says that an accelerated frame of reference is the same as a reference at stationary in a gravitational field. You can't tell the difference. So if a beam of light is curved in an accelerated frame of reference, a beam of light should also be curved in a gravitational field. How about that? But light is comprised of photons and has no mass. These photons have no rest mass. So there should be no Newton's law of gravity on the photons of light. But regardless of that, since an accelerated frame of reference is the same as a gravitational field, light should bend in a gravitational field. So Einstein proposed that a beam of light should be bent downward by a gravitational field. The bending would be small. A laser would fall less than 1 centimeter from horizontal after traveling 6,000 kilometers. But experiments have verified this effect. So, experiments show that light actually is bent in a gravitational field, exactly according to the predictions of general relativity. Here are the postulates of general relativity. The first one we've already hinted at, the principle of equivalence. And it's really broad and beautiful. All laws of nature must have the same form for observers in any frame of reference, whether accelerated or not. We took this earlier to mean inertial frames of reference, which are just moving at constant velocity with respect to each other. But now we're saying all laws of nature, physics, and everything else must be the same for any frame of reference, whether it be accelerated or not. That's the principle of equivalence, and it makes life in the universe easier to envision. In the vicinity of any given point, a gravitational field is equivalent to an accelerated frame of reference without a gravitational field. In other words, if we had a gravitational field on a planet, we could transform it into an accelerated frame of reference with no gravitational field. You wouldn't be able to know the difference, and that is one way that you could deal with gravity, is using an accelerated frame of reference with this principle of equivalence. Associated with this whole idea is a concept Einstein called space-time. Einstein specified a certain quantity, the curvature of space-time, that describes the gravitational effect at every point in space. Looks something like this. You're accounting for three-dimensional XYZ space plus the effects of time. The curvature of space-time is due to the presence of mass. According to Einstein, there is no such thing as a gravitational force. Instead, the presence of mass causes a curvature of space-time in the vicinity of the mass. This curvature dictates the path that all freely moving objects must follow. Consider it like this. Imagine two travelers moving on parallel paths a few meters apart on the surface of the Earth. They are heading exactly northward towards the North Pole. As they are walking, their paths will be converging along this surface of the Earth, and eventually they shall meet at the North Pole. They will have moved toward each other as they are walking parallel paths, as if there were an attractive force between them. But there is no attractive force between them, at least on that level. They are forced to converge because of the surface that they are walking on. So it's the geometry of the curved surface that causes them to converge, not a force of attraction between them. How about that? We can imagine the same sort of thing happening with light, that the space-time is being distorted by the presence of a mass, like a star, and that space-time is the path that light must follow. So light following that path will curve according to the space-time, the geodesic between 2 points. Hence, light will curve in a gravitational field due to the distortion of its surface. The Earth does not orbit the Sun because the Sun is pulling on it. The Earth is orbiting the Sun because that orbit is the shortest distance in four-dimensional space-time that it is constrained to follow because of the Sun's mass distorting the space-time that the Earth is in. So, general relativity summary. Mass 1 tells space-time how to curve. Curved space-time tells mass 2 how to move. And the effect is what we have been calling Newtonian mechanics, gravity, that sort of thing. Now we're just saying it's all involved. Gravity, space-time, mass, and energy. In fact, the average curvature of space-time is proportional to the energy density. Now we said previously mass and energy are the same thing. Now we're saying mass, energy, gravity, space-time, it's all intertwined into the fabric of space. Gravity, mass, and energy are all interrelated. And when we think of this way, it's all a simpler concept. The actual equation can be solved for the metric, which can be used to measure lengths and compute trajectories. Testing general relativity. General relativity predicts that a light ray passing near the sun should be deflected by the curved space-time created by the sun's enormous mass. So there might be a point where a star might be behind the sun, but because the light of that star is bent by the curved space-time of the sun, it actually will go around the sun and be perceived by Earth on the other side. The only time that you might be able to see this would be during a solar eclipse. So in 1919, which was right after general relativity was introduced, there was going to be a total solar eclipse, and the idea was that maybe we can test this theory of general relativity by observing this total solar eclipse. So in 1919, Arthur Eddington took a trip to Principe Island off the coast of Africa, because that's where the total solar eclipse is going to occur, and that year was going to be a good total solar eclipse. It's going to be almost 7 minutes long, which is long for a solar eclipse. Most total solar eclipses are going to be on the order of 3 or 4 minutes. But that one's going to be 7 minutes long. They went to that island. They needed an eclipse to block the sun so that the light of stars behind it could be seen in a picture. However, they went to that island, and even though it's going to be 7 minutes long, for the first 400 minutes of the total solar eclipse, it was too cloudy to see the eclipse and too cloudy to take a picture. Finally, for the last 10 seconds of the total solar eclipse, the clouds cleared and they were able to snap a couple pictures, take pictures of the stars and the eclipse at that time. The data they collected proved within the predictions of general relativity that general relativity was indeed correct. And they could see stars that should have been behind the sun. They could see the light of those stars in those pictures because the light was bent around the sun. Here's Arthur Eddington telling these great results to Einstein at that time, and Einstein looks quite pleased. Another paradox at that time was that it was observed that Mercury's orbit was perturbated by 1.5 degrees per century. So the orbit itself was moving, and Newtonian mechanics could not account for this perturbation. At first, before general relativity, might have been proposed that there was actually another planet on the other side of the sun, exactly in the same orbit as Earth, such that this other planet was allowing to perturbate the orbit of Mercury in such a way that this could be explained. This new planet was called Vulcan, and we would never see this planet because it was exactly on the other side of the sun from us. So as we're going around the sun, it was going around the sun. And this could help explain the perturbation. It's amazing what scientists have to come up with sometimes to try to explain things. But generally simpler is better. And general relativity was able to explain this perturbation of the orbit of Mercury, so the planet Vulcan was allowed to fade away. So basically, the planet Vulcan did not live long and prosper. Too bad. Here's Einstein's cross. These 4 spots you see in this picture are images of the same galaxy that are way beyond the central aspect of this picture. There's a large mass object that is allowing the light to be bent from a distant galaxy and hence, in a sense, be focused to our observation. Otherwise, we wouldn't be able to see that distant object. So, in a sense, this is acting like a lens to further objects. Gravitational lensing. So the massive object is a lens that allows us to see further into the universe. Here's a similar configuration. Evidently there's a massive object in the center and there's a large gopher much further beyond, allowing us to see this gopher to our observation. Einstein's gopher. Now here's an example of gravitational lensing, and the streaks you see in this picture are the lensing caused by large gravitational objects allowing light to be bent to our observation from far greater distances. Black holes. If the concentration of a mass becomes great enough, a black hole is believed to be formed. The curvature of space-time is so great at a black hole, within a certain distance from the center, all light and matter become trapped. The radius is called the Schwarzschild radius and also called the event horizon. It will be about 3 kilometers for a star the size of our sun that collapsed into that singularity, and hence this radius would be 3 kilometers away from that point. The center of the black hole is called the singularity, point of infinite density and curvature where space-time comes to an end. Black holes were kind of a mathematical construction from general relativity, but we now know that they do exist, and in fact they are the driving force behind in the center of every galaxy that we see. So as you look in the galaxies, in the center of them are black holes. Is that the crack in Einstein's theory of relativity? Nothing's perfect. Gravity waves. Major events involving massive objects might cause ripples in the space-time fabric. These gravity waves are being searched for. Really, to be observed, one of the best things to try to observe is the explosion that we call the Big Bang. That's when space expands so rapidly that it should have produced gravity waves. So we're looking for that, and one of the things looking for that is the Laser Interferometry Gravitational Wave Observatory, or LIGO. Here's LIGO. There's one observatory in Hanford, Washington, and one in Livingston, Louisiana. And what they are interferometers based on the suspension of mass. And so you have a laser that will bounce off one mass and then split and bounce off another mass. And if those masses move, then the interference pattern you see should shift. And they might move under the action of a gravitational wave. So we have these 2 setups looking for it. And the reason you need 2 is for redundancy. If one were to observe a gravitational wave, the other one should observe it as well, and then we know we actually have a gravitational wave, as opposed to maybe a truck moving down the highway nearby causing the same ripple. Because that's how sensitive these things are. So they have to eliminate any of these other possibilities for observation. Looks something like this. The interferometer, we have these test mass and other mass. The laser beam is split and interferes on itself, and then you detect the interference. It looks something like this. This is relativity explained by M.C. Escher. This is not LIGO. No, I'm confused. This is LEGO. This not quite the same thing. Now, if we were to look inside LIGO, it would look something like this, where you have evacuated paths where the gas could not cause the vibration, and everything's set up so that hopefully someday it will detect gravity waves. Well, a much better setup actually has detected gravity waves, at least since a couple of days of recording this video, at the South Pole. The BICEP telescope, which is looking at the background cosmic microwave background, should be able to discern a polarization in that background due to the absorption of atoms from the light coming from the Big Bang. And that is the cosmic microwave background. Light is scattered in our atmosphere due to absorption in the atoms in our atmosphere. We see that light as being polarized. The same thing should happen to the cosmic microwave background. And in fact, as of this screening, it has happened. And they have observed those gravitational waves. It's a landmark event which should prove the Big Bang theory. So here's our cosmic wave background. Seeing polarization in that background is proving gravitational waves. It also proves and brings together the ideas of general relativity and quantum mechanics. Merges those together, which up to this point have been pretty separate theories. Here I am explaining this great result to Einstein, and he looks quite pleased with the results. Let's go on and look at quantum mechanics.